Yeah, hello again. Hello there. We're back. What's up, Sid? Oh man, I'm low-key like really pissed at Spirit Airlines. Surprise. So my flight that I had to like again reschedule lecture to do 2 lectures today, you know, just got canceled. And I'm like, God, what? You just canceled my flight? I had to move so many things around for this flight, and now you cancel it. So I'm like, oh, it literally happened like 15 minutes ago. So I was like, oh, we could just do lecture at the regular time, but I'm not gonna. I already prepared for the whole thing, so it's okay. But that'll be my job after this, is to go yell at some customer service agent to try to get rebooked on something. Yeah, anyways, okay. It's alright, life happens. We're gonna do dipoles today. And because I never got to teach dipoles when we did electric fields. And then I also want to do some more intense type of figuring out like the net charge on conductors and non-conductors based on like electric fields and stuff. So let me get all that ready for you guys. Just vibe out a little bit for now. Is the test going to have 2 30-part questions again, you think? Yes. Most likely. What did you guys think of the format? 4 multiple choice, 4 like kind of shorter free response, and then they call them scaffolding problems when you have like something where it's like part 1, part 2, part 3, and they all build on each other. That's called a scaffolding problem. So yeah, 2 30-point scaffolds. I guess the advantage is if they cancel my flight, I have all of Friday to, I mean, well, they already canceled my flight, but if I can't get another flight, the advantage is I have all of Friday to do all the regrades. I was planning on doing them at the airport or like, you know, in the whatever car ride when I get on the other end. But I guess that's not happening now. It's okay. I guess it depends on how the test goes. Yeah, I guess it does. All right, let me just double check what we got for questions. Then we'll start in like a couple minutes. How the new one goes, yeah. Ooh, okay, cool. Yeah, we'll do a little bit of dipoles, and then we're going to do non-uniform charge densities. Or I guess it's uniform charge density. Yeah, okay. And then one of them is non-uniform. Oh, okay. Ooh, and this is a big one. Okay, cool. All right. I know what we're doing. Let me clear this. welcome. Today we're going to go over a little bit of dipoles and a little bit of calculating Gauss's law and electric fields for more complicated geometries. As a little bonus for y'all that are tuning in tonight for Late Night Physics with Dr. G, you can expect one of these questions to most definitely show up on the exam. Yeah, I promise that something we do today will show up on the exam. So if you go through it and you learn, you get some points. So congrats to showing up. Let's talk about dipoles. Okay. Dipoles. Okay. So, yeah, and a dipole occurs whenever you have two charges that are equal and opposite, and they're like pretty close to each other, okay? And the location at which they are is pretty constant, okay? They're not moving, they're kind of in equilibrium, right? And as such, like, this dipole exists without a field, and it doesn't break apart in the presence of another field. So, for instance, if you had, you know, I think some famous dipole moments, right? Would be those. Where's like another cool one? Yeah. CO2? Well, CO2 has no net dipole. Where's just like a single, yeah, okay, there we go. Can I just do like N and F? Yeah. I want to see where I see the clouds. Clouds. Helium atoms. Where's like just basic? Sure, I guess we could do HCl. But I want the picture with it too. Fine. But okay, actually, this is actually a good example one. Yeah, and then here. So, okay. Examples of dipoles in our life, right? Water has a permanent dipole moment. And what that arises from is that hydrogen charges are positive, or hydrogen atoms are positively charged, right? Oxygen is negatively charged. You learn in chemistry, right, that oxygen has like a -2 oxidation number, and then hydrogen has each has a +1, and that's why this balances out to be neutral. But in doing so, there is some like symmetry to this, right? Because this molecule is in a bent configuration, the component in the x direction ends up canceling out, and all you get is this dipole moment that acts straight up in the z direction. Now, in chemistry, dipole moments point from positive to negative. In physics, dipole moments point from negative to positive. There are always like some little things that chemistry and physics just decide to not agree on. So a little note in chemistry. Dipole moments point from positive to negative. But in physics, which is the class we're in, they point from minus to positive. Okay. So what we can think about is, let's say, for instance, this simple dipole moment of a positive and negative charge, which, let me get like an easy picture of that. Here, this is great. Actually, I really like this, actually. This is a great one. Yeah. Let's say that this thing is in the presence of an electric field. Okay, let's say there's an external E field pointing here. Okay, external E field. And that this dipole moment or this dipole thing with a dipole. Oh, do I have to copy it on top of it? That's annoying. Okay, there we go. Happens to be at like some sort of angle. Okay. We're gonna kind of describe what happens here. All right, so let's put it. Let's put this like this. Okay. So in this case, if the electric field is, and actually, let me have the electric field point the other way. I think it'll make things a little bit better. Sorry, we're gonna do this way. What's up, boss man? Teaching some physics tonight. Okay. So if this is an electric field, remember that electric fields are usually generated by some sort of background positive charge thing here. On the right, usually that would be an infinite sheet of charge, and then you have some negative charge thing here on the left. Okay. We can think about what the individual forces would be on the different parts of our dipole. So the positive part of the dipole, right? This is think of this as like a positive charge. This is going to feel a force from the electric field. Remember that force is equal to QE, okay? So if E is pointing to the left and the charge, in this case hydrogen, which is positive, is here, then the force on it will also be in the same direction as the electric field. So this is what we would call F plus, maybe. Yeah, textbook calls it like F plus. However, the negative end of our dipole over here is going to be pulled towards the positive part of the electric field, is what I say. So that'll be creating a force that is opposite to the direction of the electric field, because now this is a negative charge. And so that's going to create a force in this direction, F minus. Now, what you should notice, right, is that there's kind of a torque that's going on here. If we define, move this up, the distance between these two things to be d, okay, then we can go back to mechanics and think about that there's some sort of rotation point here at the center, okay? And then this is going to be located a distance, right? D over 2. If we were to calculate the torque, right, on each component, right? Remember that torque is equal to R cross F, all right? So that would be equal to D over 2. And let's, we got to come up with our directions here. R. Have you guys remembered cross products? I think you probably did in mechanics at least. Definitely in vector calculus or something. But if R points this way, and F is pointing this way, then it's into the page. So that's negative. Okay, so this is negative D over 2. Cross F. And then, yes, the right-hand rule, right? Yes. Remember the right-hand rule. It comes up a lot. Especially when you guys do magnetism, it's all right-hand rule. So the electrostatics portion of this course, which is 1B, tends to be a lot of dot products, which you don't need to do funny rules for. When you take 1C, it is all cross products. And so it's a lot of right-hand rule stuff. Anyway, so you have a torque here from this. And then you also have positive D over 2. Let's say this is crossing with F minus. Crossing with F plus. Okay. Basically, like, we have to define some direction for positive D over 2. I don't care what it is. But then we remember that F minus, right, was equal to negative QE. Because the force on the negative charge pointed opposite to the electric field. And so we can say, okay, negative QE, sorry, negative d over 2 cross negative QE. And then there's an additional torque we have from the positive one, and that's going to be positive d over 2 cross positive QE. Well, look at this. These two things will cancel with the minus signs, right? You like dot products? Well, yeah, this class is all dot products. So you end up getting d over 2 QE, d over 2 cross QE, d over 2 cross QE, and that gets you a total torque on the entire system, which is just equal to Q d cross E, where the convention is for this, we say D points from the minus charge to the positive charge part of the dipole. Yeah. That's kind of what we did. We did here, yeah. Yeah. Okay. Right. Because in here, we defined this as like negative D. So we defined positive D going from here to here. So measuring this distance is minus D over 2. And then here, this ends up being positive D. And it has to do with how the right-hand rule works. You always want like into the page to be positive. Or sorry, into the page to be negative and out of the page to be positive. Just as like right is usually positive and left is usually negative. I guess I kind of messed up here because I made E to the left. In general, all the negative signs eventually flip out. And this is the main thing that you want to know. Is that the torque acting on a dipole is going to be equal to the charge of that dipole. And when we mean charge, we mean just like one of the ends. Assuming that the dipole is equal and opposite charges. Times this d vector, which is the dipole moment. So this is the dipole moment. Crossed with the electric field that it's in. And what you should see, right, is that as this side is trying to get pulled this way, right, there's a net torque on this object, right? This is trying to get pulled this direction, which means it's trying to rotate clockwise. And if this side right here is trying to get pulled this way, it's trying to pull it also clockwise. That's why there's a twist. Correct. Yes. You have two ends, and then the forces are in opposite directions, right? You have here and here. And what that does is that ends up straightening this thing out such that it lines up with the electric field. And again, if this is the positive end and this is the negative end, notice how the dipole moment, which points from negative to positive, will now point in the same direction as the electric field. So another important thing with the cross product here, right? So cross product measures how much perpendicular amount of one vector is in the amount of the other vector. So if two vectors are perpendicular, the cross product is perfect. It's equal to the magnitudes. If two vectors are parallel, then the cross product is 0. And that comes from this. We also, this is another little vector cal moment. We learn, right, that A cross B is equal to the magnitude of A, magnitude of B, sine theta. And really, sorry, this is the magnitude of A cross B, because A cross B is a vector. But a lot of times, we figure out the direction, kind of just eyeballing it, being like, oh, if it's going right and it's going up, then it has to be coming out of the page if we cross product it. But the magnitude of it, you see here, is equal to A, B sine theta. So if A is parallel to B, then theta equals 0, and the sine of 0 is 0, and this whole thing goes away. So, yeah. Kind of a cool thing. Dipole moments. I think we end up actually calling this QD the dipole moment. Okay, they call P equal to 2B. All right, so my bad. Sorry, the whole thing here is the dipole moment. So, vector P, which equals QD, that's equal to the dipole moment. And it's proportional, right, to the amount of charge in the dipole and the distance between the two poles in the dipole. And then the torque is defined as P cross E. Yeah. That's where this comes from. Okay. I think we have a clicker question on this one. I did do a clicker question with some dipole stuff. Yep. Okay, cool. Let's see it. Lecture 17 clicker. Let's pull this first one in. Correct, yes. So the dipole moment points in the same direction as the direction vector, as D. The only difference is the dipole moment also includes how much charge is on like the positive end of the dipole. All right. One sec. Where's my stuff? Okay, and then this was clicker 17. Ooh, okay. So it says, you place a dipole in an electric field with the field lines as depicted. What happens to the dipole just in general? Okay, cool. So dipole moment, right, is going to point from negative to positive. That's going to point in this direction. The E field, it's interesting. The E field is like kind of curved up here, but then eventually it does this, right? E field is going in this direction, okay. And we know that the dipole moment always wants to kind of line up with the E field. So it's for sure going to try to rotate clockwise. Okay, so we can get rid of anything that says counterclockwise. Definitely not going to be this. Definitely going to not be this. Definitely not going to be this. Okay. Because, again, torque is equal to P cross E. And so there's some component of this which is perpendicular to this. So you end up getting a torque that tries to move that in this direction, to rotate it. Remember, for instance, if torque is out of the page, so this represents out of the page, that represents rotation in this direction. And if torque is into the page, that represents like this direction. And this is torque into the page. This is usually negative. This is usually positive. Okay. So because, yeah, P cross E points into the page. And again, you want the amount of P that's perpendicular to E for a cross product. So I don't care about the horizontal component of P, right? Because that's parallel to E. All I care about is the perpendicular component of P, which is this. And that points up, right? Because if this is pointing up and to the right, the vertical component points up. P's up, E is to the right, and so your thumb goes into the page, and that means you have negative torque. And when you have negative torque, that corresponds to wanting to rotate something clockwise. This comes from like it's like the curl hand rule. What is it? It's also the right hand rule. Yeah, you learn like this. There you go. This is it. This is curl. Yeah. The curl right hand rule. So if you were like to curl your hands, and make sure you're doing it with your right hand. If you do it with your left hand, you get the exact opposite result. But wherever you curl your hand around something, the your thumb sticking up, that's like the product of A curling and B. Yeah. And then yeah, they learn this. So this is the standard one. This is for like if you have just vectors that are perpendicular. You're like, okay, cool. A's there, B's there. A cross B points up. But A cross B can kind of be thought of as like a curly movement, which is the same thing as this. Yeah, these are kind of like the two of the same things. So going like this is the same as going like this. You still always like have A cross B pointing up. Okay. Yes, and this is what you'll eventually use it in E&M. F equals QV cross B. This comes up a ton. That's a 1C concept for sure. Okay, but we also had to ask about, okay, but we know it rotates clockwise. Is it going to move? Interesting. So from what I see here, do you notice how the lines here are closer than the E lines are here? The amount of like how close the electric field lines are to each other, that represents the strength of the electric field. So what we say here is that like E is strong here and E is weak here, right? Because the field lines are further out apart. You should also notice this if you ever do like the electric field lines of a point charge. Yes, I want like a better diagram of it. Oh, I know what I want. Electric field lines of 2-point charges. But I want 2 different values of charge, two different values of Q. I think this was a homework question we did at some point. Yeah, here we go. This is what I want. I want this. Okay. So for instance here, these are the electric field lines produced by a plus Q charge and a minus 3Q charge. Remember that for positive charge, electric field lines move out, right? That's why we have these out arrows. And that for negative charges, field lines move in, okay? But the amount of field lines, or like how closely spaced the field lines are to each other, is also indicative of how much strength you have in the electric field. And if you remember that E is equal to KQ over R squared, then you also know that the electric field is also proportional to the amount of charge there. So in this case, this Q here, right, has just 6 field lines going about it. And so this is kind of a weak field. This, if I counted all of these, would probably have 18. And it's to represent the strength of the electric field. So we say like strong E, weak E. And so in this case, the electric field here must be weaker than it is here. So since so once this thing rotates, okay, notice that the positive end of this dipole is closer to the stronger end of the electric field. That means you're actually going to get a difference in forces on it, right? So the electric field is always generated, right, by some positive here and some negative kind of here we can think about. But the negative here is stronger, and it's going to pull this more this way than this will pull the negative end this way. So in that case, this dipole moment should also move to the right, because it's not in a constant electric field. The electric field is changing with position. So I believe this is answer choice A. We can go check that out. And do we get it? Yes. Okay, nice. All right, I'm going to leave this for a second and let the chat catch up if there's any questions on it. And then we're going to do a little bit harder geometries for using Gauss's law that I didn't get to go over in class yet. Hooray! Yes, nice, Brian. Love that. Okay. Here we go. Next question coming up. All right. Here, we say a rod has a length 4L and uniform positive linear charge density lambda. The rod is held at rest on the x-axis in the orientation as shown. Position P, not shown. So some position P, not shown, is located on the x-axis, a distance xp from the origin. And we're doing wherever this x of p is at least greater than 4L. And what they're asking us to figure out is what is the electric potential at some coordinate that is away from this. Right? Okay. This is kind of a cool question. I like this one. Okay, so one way to think about this is we know that the potential from a point charge surprise stream, yeah. Jeff, this is my stream because I had a flight that was going to interfere with my stream tomorrow, but I just found out an hour ago that that flight got canceled. So I don't know. I guess the universe just wanted me to stream early. I'm like, okay, fine. To a distant point, let's say to a distance r. We remember that is equal to kq over r. Right, that's for a single point charge. Okay. So if I had a single point charge here and it was q, then the potential at any point p here would just be equal to kq divided by r. Now, where things get tricky is now I have a continuous charge distribution. So I can think about I have a lot of these little q's all right next to each other, and they're distributed from 0 to 4L. Okay. We do at least get the charge density, which is nice. I do like that. That's great. Okay. So in the case where q is not discrete, when we're not adding up the kq over r's, you know, of individual point charges, we can represent this as an integral, right? And I can say, okay, well, v at some position r is equal to k times the integral, and then that's going to be dq over r. Okay. And then dq represents what little bit of charge we have that we're looking at. And so, for instance, that little bit of charge, we did this in the early example with the line of charge, but we were figuring out the electric field here. That dq is equal to lambda dx. Okay? So now we can replace this with is equal to k integral of lambda dx all over r. Okay. And instead of saying r, I think, let me think how I want to do this. Let's define some point here. Okay. And then, oh, x, right? X, we said, was always being measured from the origin. Okay, that's important. So when I'm calculating my v of r, so actually, let's not do v of r. Let's say this is v of x. Yeah. X is the distance from the origin. R, this is the distance from my dq, or my lambda dx, to where I'm measuring the potential. And so what I notice, right, is that if I'm measuring the potential here, right, let's say we had a couple independent, just single point charges that were located here. And I just started, like, adding them up, okay? R is going to refer to this. This is R. And then this becomes R. And then this becomes R. So, X, so R, let's say this is where my point is. Let's say this is at position XP. So here, we should make this, sorry. Let's make this as a function of XP. XP is where we're measuring the potential. But then lambda dx, that's going to decide, like, in terms of x, where we're integrating charge. And for right now, I know dx is going to integrate charge from 0 to 4L. Okay? However, okay, so this is going to be x. Looking at this, right? Let's say I'm looking at this specific bit of dq, which on my bounds here, right, is somewhere between 0 and 4L. All right, let's say this is, we're looking at this little bit of dq, lambda dx, okay? That's located at some position x, but r, which is the distance from the charge I'm integrating over to where I'm measuring my potential, that's equal to xp minus x. So here r is equal to xp minus x. So here, I need to replace this as potential at a point P is equal to K, e to 0, 4L, lambda dx, and then this is the integral from over xp minus x. Okay. Are we good so far in this? I can run through it again if it gets a little bit confusing with how many different x's and r's we're dealing with, right? Yes, the xp minus x. Yeah, let me do it. Totally cool, Sib. Let me do it. All right. Yeah. Here, let me, because I have like too many things written. Okay. Okay. So electric potential VP at position XP, right? That's going to be VP as a function of where XP is, okay? If this was just, let's just say, for instance, this was just a point charge. Right here, okay? And again, let's say this is x equals 0, right? This is x equals 4L. But let's say we just have a single charge there at the positive end, right? Then this would just be equal to K, and then it would be Q over X, XP, which is over R. So R is the distance from charge to potential measuring point. Okay? So if I'm measuring my potential somewhere out here, let's like say some XP. Notice how XP is R. That is the distance from the positive charge to where I'm measuring the potential. Where things get tricky is if I start integrating some amount of my charge as I start going this way. If I start adding up all the different charges along the rod. So let's say we have a charge here, right? And then let's say we represent the rod as a charge in the middle. And then we represent it as a charge at the end. Let's do a super simple model here. So we took our rod and we're representing it as 3 charges. One at the beginning, one at the middle, one at the end, okay? If I wanted to find the potential at XP, that would be KQ over R for the first one. But R for the first one is just XP. Plus KQ over R for the second one, right? The second one is located a distance 2L. So this new R, right, the distance between this charge and where I'm measuring the potential, that's now XP minus 2L, right? Because XP refers to this whole distance, 2L represents this distance, and so the distance from the charge to where I'm measuring potential is now XP minus 2L. And then let's say we add the third charge over R3. That would now be XP minus 4L, right? Because this distance here, this is R3, this is R2, this is like R1. Do you see how the distance between where my charge is and where I'm measuring the potential starts to go down as I start adding up the individual charges along the rod? Good. Okay. So now I'm going to do this in the continuous form. So I'm going to say, okay, instead of doing like individual charges here, we're going to say VB x of P is equal to K, and we're going to integrate from 0 to 4L. And now my charge is not individual Qs. It's lambda dx's, right? It's little charge densities times widths, okay? And now the distance from these little chunks to where I'm measuring my potential, that's now going to be XP minus X, because X here refers to me integrating from 0 to 4L to get the total charge on the rod. Sometimes, like, yeah, going to, like, a simple, like, point charge model and then expanding it to be, like, oh, what if we had, like, 1,000 charges representing this rod? It makes a little bit more sense. I'm glad you brought that up, Sib. Because, yeah, honestly, like, this was starting to confuse me. Like, we're drawing too many things here. This makes more sense to me. Okay. So now we can just integrate this. Okay. So this is going to be K lambda integral from 0 to 4L dx over xp minus x, right? Xp is just a constant, right? Good explanation. Yeah, thanks. This integral is ln. The integral of dx over x is equal to ln of x. Okay, so really you just do a u sub where here's what we say. We say, like, okay, u is equal to xp minus x, so du is equal to xp. Or sorry, derivative of xp is just 0, so that's going to be negative 1 dx. So then dx is equal to negative du. Okay, so this becomes k lambda integral from, oh, don't worry about the bounds yet. And then we're just going to say negative du over u. Integral of du over u is ln of u. So now I have k lambda ln of u, but then I replace back in what I have. So that's k lambda ln of xp minus x. And then that is evaluated from 0 to 4L. This is where I put the bounds back in because I've transferred back from U land to X land. And what do we get? We get k lambda ln of xp minus 4L minus k lambda ln of xp, which is the same thing as k lambda. So if you have logarithms that are subtracting each other, they're dividing. K lambda ln, and then that's xp minus 4L all over xp. Or, yeah. Maybe it's this too. Maybe k lambda ln of 1 minus 4L over xp. That could work too. Let's see if what the answer choices were for this one. Dun, dun. Oh, and I think I'm missing a minus somewhere. Oh, my bad. Sorry. Negative du over u. There's a minus sign here. Sorry. There's a minus sign here. I see. Good. If the charge density is uniform, why do we still need to integrate to find the potential? Can't we just use total charge times some distance? So you can't, because the distance is changing, right? The total charge, like the location. So you could with a sphere, right? This is only the sphere thing. If you have a sphere of charge and you're outside of it, you can think of it as a total charge just straight in the middle. This does not have the same symmetry. A rod is not a circle. Yeah, because it turns out, I mean, I wonder, could you approximate this as a single charge here? No, no way, because like we got LNs and stuff going on, right? Yeah. That's an interesting idea, Min, to think of like, oh, let me think of this whole rod here as just like a single charge located at 2L and then just find the potential. I think the issue is that only works for spherical geometries. Oh, and Jeff brings up a good point. He says there's no fixed point on a rod that would work for all distances. Okay. You can't just pick some position here and it'll end up approximating the thing. Because, like, what happens if you're over on this side? I mean, that's good intuition to maybe do that. Okay, so wait, I messed up my minus sign here, though. So, sorry, there was a minus sign here, which means this is now minus. Yeah, XP is not moving. Well, this is a function of XP. Sorry, so this moves away, right? This is going to be now XP divided by XP minus 4L. I think that's just how that stays. And then, let me get the answer choices. 1 sec. Where'd they go? Where are my answer choices? Oh, there they are. Yo, what's up, Walking Stick Library? Good to see you. Sorry, I'm putting this in real quick. We're doing some physics today. Okay. So this was XP, so get rid of this. This is wrong. Pull it in. There we go. K lambda XP over XP minus 4L. That's answer choice D. Let's see if that works. On here. D. Correct. Nice. Cool. Yes, and so, Sib, this is still a function of XP. So, V of XP is equal to this. So notice how, like, as you vary the distance, you do still vary what the value of the potential is. And actually, pretty cool. Let's think about, like, as XP goes to infinity. Interesting. This like kind of goes away, right? And then you just get the ln of 1. Oh, and the ln of 1, good evening to you, walking stick. Ln of 1 is just 0, right? And this makes sense. The potential should be 0. This is always a good thing in physics. Anytime you get a result, try taking limits at different infinities to see if it makes sense with what the world says, like with reality. So we know that as x approaches infinity, that the potential of stuff should approach 0. And for here it does, right? If I take the limit as x of p goes to infinity for k lambda ln of xp over xp minus 4L, well, what I can do, this is a cute little limit trick I use all the time. Because you could do L'Hopital's rule, obviously. But if you plugged in infinity for xp, you get infinity over infinity minus 4L, which is bad. Can't really have infinity over infinity. But a nice little hack is you just divide everything by the thing that you're kind of like annoyed with. So I'm annoyed with XP here. I'm going to divide the top and the bottom by XP. That's totally legal. I'm allowed to divide the top and the bottom by the same thing. As long as that thing is not 0, which XP is not 0. So now I get KP ln. XP over XP is 1. And then this is over 1 minus 4L over XP. Now, the limit as XP approaches infinity, watch what happens. This infinity only affects this. And so what you end up getting is 1 minus something divided by infinity. Anything divided by infinity is 0. So this goes away. And now we're just left with k lambda ln of 1. And the ln of 1 is 0. And so this goes to 0. And this makes sense, right? The potential should go to 0 as we get really, really far away from the rod. It's a good way to just, like, double-check yourself. Cool. I really like that. That's a fun question. That could come up on an exam. Because it's so fun. Okay. Like, Dr. G, that wasn't really fun, man. Like, I can think of things that are a lot more fun. Potential and charge? Yeah. So, charge is like a characteristic of something. Like how much mass something has. Potential is related to, like, the field it generates. So, again, think about something with mass, right? Something with mass, if it has more mass, creates a larger gravitational field. And thus, when you move things away and, like, towards it, you change the amount of energy that's stored in that. Yes, the charge between two particles is 1 over d squared. Correct. That's Coulomb's law. But then potential is 1 over d. And that comes from integrating the electric field times the distance in what I forget what this law is called. But it's E dot dl is equal to V, or negative E dot dl. Yeah. Potential is the integral, correct. It's really the work done is where it comes from. Yeah. And the weird thing about electricity stuff is technically there's also electric potential energy, which is different than potential. That's what we did last week, was kind of going over that. Okay, let's see. A solid plastic sphere of radius A and a conducting spherical shell of inner radius B. So this is a shell, right? Shells have like a thickness to them and then like a hollow part in between. Are shown in the figure. The shell has an unknown charge. Okay, so this, we don't know what this is. We're like, Q equals what, right? The solid plastic sphere has a charge per unit volume of beta R. Okay. So this is plastic, which is an insulator. It's not a non-conductor. So this is equal to beta R. Okay, express all your answers in terms of variables. This happens a lot in physics. They don't give you numbers. They're just like, yo, dog, just play with the letters. I'm just getting you ready for like what upper division physics is. Okay, let's try to do this first question. It says, consider a Gaussian sphere radius r concentric with the plastic sphere. Derive an expression for the charge enclosed by the Gaussian sphere for the following regions. R is less than R. R is between A and B. Okay, cool. So the charge enclosed by like our Gaussian shape. So we've done this a couple times. I'll rederive it really quickly. But if you have some Gaussian shape here, and this is for it being the R is less than the radius of the conducting sphere, we know E times 4 pi R squared is equal to Q enclosed over epsilon naught. The Q you enclose is going to be equal to here, let's just do it separately. So Q enclosed is going to equal the integral from 0 to some location R of 4 pi, or let's just call this like RA, 4 pi R squared times rho dr. This is like, this part right here is the dV, and this is rho, and then rho dV is equal to like Q total. So rho in this case is beta R. Okay. So we have 0 to RA, 4 pi R squared beta R dr. So now this becomes 4 pi beta integral from 0 to RA, and then that's R cubed dr. And if we integrate this, this is going to become R to the 4th. Right? So 4 pi beta, and then this is going to be R to the 4th over 4 from 0 to RA. And RA is just our location we're looking at. So I'm just going to substitute that in. And then, so cool. 4 pi beta RA to the 4th over 4. Nice. Now, for the charge being enclosed from A to B. Okay, well, this is all open space. So as I go further and further out, I'm not enclosing any more charge than what was enclosed when I went all the way out to radius A, right? So this right here is the amount of charge enclosed from RA is between 0 and A. But when I get all the way out to A, so we say Q enclosed at A and less than B, like in that in-between area, that's just going to be 4 pi beta A to the 4th over 4. Okay. I think that's good for that, so let's see. Answer choices were... So I think this matches... So wait, part 1 was less than A, and then the other one's in between. That's going to be this one, right? That matches up. RA is just R in their case. Okay, so let's go back here. Let's choose choice A. Correct.
My man.
Okay, and then it says use Gauss's law to determine the magnitude of the electric field. Okay, well, we were already doing that, right? This is what we were doing when we were doing electric field. So we know that in order to calculate the electric field, you just take Q enclosed and you just divide it by 4 pi R squared. So in part A here, we derived equations for the charge enclosed in different areas. And then we're just going to divide by 4 pi r squared to get our electric field. So E is equal to 1 over 4 pi epsilon naught. And then it was Q enclosed over r squared. So in part 1, just within the center with the radius A, and part 2 up until the radius A for part B. I think you mean like part 2, not part B, right? There's technically like 2 parts to the part. So there's 2 regions, right? Are you talking about like region 1 and region 2? And I think you're correct, Sid, with what you're saying, which is, yeah, for region 2, the charge enclosed is just up to A, because you don't enclose any more charge as you go further and further out, right? As you go further out this way, you still only just enclose this much charge. No, you're good. I understand what you're saying. Thanks, Sid. Yeah. So, right. So for R less than A, that's going to be 1 over 4 pi epsilon naught, and then Q enclosed there was pi beta r to the 4th over r squared. So this goes away. You just get r squared. And that's for r is less than A. And you'd have 1 over 4 pi epsilon naught. We're going to get to the shell. Yeah, so they only asked us for the electric field up to B. We haven't even gotten to the shell yet. I think there are 4 parts to this. Which we got to do in 12 minutes. We'll do it. Don't worry. We're going to get it. Okay. This was pi beta a to the 4th over r squared. And that was for r is less than A, less than B. So it's kind of cool. So here, right, electric field goes up as you get further away from the center, because as you're moving in the sphere. And then electric field drops as you start going out. So if I wanted to make like a graph of this so far, right? And this is r squared, which is interesting. So let's say this is r, and you go from 0 to A to B. Going up from 0 to A is going up exponentially. That's over r squared. Going out, now you're going as 1 over r squared. So this is going to start dropping in this direction. That's kind of cool for electric. We might need this for other things. Okay. Part 2. All right. R squared, nothing else. This one works. This one works. I need the 4 pi epsilon naught. And then here I need a to the 4th over r squared. Okay, cool. Answer choice D looks correct. For part B. Nice. Ooh, very cool. Part C. Now we're dealing with the shell. Okay, it says at any point outside the conducting shell, it is observed that the magnitude of the electric field is 0. So this should tell us something, right? If the magnitude of the electric field is 0 outside the shell, what does that tell me about the charge that's being enclosed outside the shell? Right? E equals 0 out here, which means that the charge enclosed has to also be 0, right? So kind of a cool thing here. Let me get a picture. Let me get rid of this. So if E is 0 out here, then also Q enclosed must be equal to 0. So we know that you enclose positive charge here, right? And we calculated how much charge was enclosed there. That means you have to then enclose negative charge on the shell. And the charge here has to be equal and opposite to the charge here in order for the electric field outside to be 0. That's really cool, actually. Huh. Okay. All right, so let's remember how much charge we said was enclosed just on A. That charge enclosed was this, right? Because that's once we got all the way out to A and up to B. So we remember that, okay. Q on the plastic was equal to this. So that's some positive amount. That means there has to be some negative amount on this. And then how this is going to work, since this is a conductor, guys, you're going to have negative charges, I believe, like pooling on the inside. Oh, and then there should be, I think there should be 0 charge on the outside. Yeah, equal and opposite. Yeah, very cool. Right? This positive charge, so electrons are free to move, right, within a conductor. And so they are going to all be attracted to this wall of the inner shell. Oh, very cool. So on the inner shell, it's just going to be this, but negative. And on the outer shell, it's going to be 0. Wow. I think, oh, that's super cool. I remember this was the answer, but I forgot, like, why it was. Okay. So in this case, outer has to be 0. Inner, oh, the 4's cancel. Great, yeah. Pi b over 4. Answer choice C should be the correct one. Nice. Okay, last part. Okay, 4 points, W, X, Y, Z. Rank the points according to the electric potential. Okay. No, so there is no charge on the outside of the shell, Sib. So this has a charge of 0, and the inner side of it has a negative charge. Overall, the shell has to have an overall negative charge, because when I enclose this, I need the negative from this and the positive from this to cancel out, such that I have no E field. But what we say is that, like, all of the negative charge in the conducting shell is going to be brought towards the positive charge. Sorry, I didn't have my screen on. Sorry. Yeah, sorry. The inner wall here is negatively charged. The outer wall is 0 charge. But overall, the whole conducting spherical shell has a negative charge. Because as I measure the electric field outside, that is 0, which means the charge enclosed, the negatives and the positives here have to cancel each other out. Does that make sense? And actually, let's use that now to, like, update our electric field graph thing, right? So let's say A to B, and then there was something like to, and then there was also B to C, and then afterwards. Yes, the inside of the conductor is also 0, right? Yeah, the inside, the electric field of conductors, like the direct inside, is always 0. When I say inside, I don't mean the inside wall. I mean like inside, like in the in-between land of the shell. Okay, so let's remember, this went up as like 1 over r squared. Then it decreased as 1 over r squared. Then the electric field has to go to 0 between B and C. And then I think it just keeps going at 0, right? Because we said the electric field outside was also 0. And actually, yeah, so this actually comes from a previous AP exam. I'm looking at what their solution was for the electric field. Kind of cool. They get the same thing. I always love when I like come up to the same conclusion. Yeah. This is what they had for the electric field. Okay, but we want to measure the potential. Okay. So let's remember that potential, right, V, is equal to the negative integral of E dot dl. Okay. And so if we're coming in from, let's say we're going from infinity, right, to some location. Yeah, this is AP, yeah. To some location, I don't know. Let's say like out to Z and out to Y. There's no electric field here, right? So as you're coming in here, there is no electric field, so you're not building up any potential. So the potential here and here is going to be 0, right? But it's going to be the same. So I would say that like Vy and Vz are equal to 0. Yeah. Okay. Now inside, right? We know there is an electric field. And that the electric field decreases as we get further towards the edge. So what's going to happen is, as we get closer in, we're going to start integrating more electric field as we go this way. And so the potential should be greater at x. So Vx should be positive. And then once we get to A and we start adding, we're still adding more electric field, it's just less and less. So then VW will be like even greater. So I think it should go W equals 1, X equals 2, Y equals Z equals 3, right? They said rank the numbers or something. I think that's what they said. Oh, did we not? Oh, sorry, we didn't put that question. Let me put the text for it so you guys can see it. Sorry. I thought for sure I did. Yeah. So it said, yeah, rank the highest electric potential with 1 and all the other ones, subsequent ones, as lower numbers. Okay, so let's see what our answer choices were. Kind of tricky here. They said rank it like 1, 2, 3, right? But they kind of said like 1, 2, 3, 4. So you had to be clever enough and notice that the potential at Z and the potential at Y are the same, and they're both low. And so I think, yeah, the correct answer here is E, right? Y and Z are both low potential, and they're the same. So they both get the rank 3 instead of 1, 2, 3, 4. This would be like a common mistake. Okay. Answer choice E. Correct. Nice. We did it. Late night physics. Serving up only the smoothest electric potentials and dipole moments. Select Dipole Moments brought to you by NPR. Well, actually, NPR not anymore. They just lost their funding. Anyways, okay. Cool. Any other questions about this? Again, thank you so much for coming out and accommodating this, even though now I'm realizing this is, you know, probably not even necessary because I don't even have a flight to get on tomorrow. I guess it's just how the universe works. But I kind of enjoyed this. So I hope you did too. If you're watching the recording, please, make sure you went through this and answered the clicker questions, and also study these questions because one of these is very likely to show up on the exam coming up next Friday. So pay attention, you know, focus, and otherwise enjoy your weekend. I will post a new chapter probably on Sunday for us to start going over. Hope you get your flight back. Yeah, thanks. We'll see. Maybe it's a sign I'm not supposed to go. But yeah, we'll post a new chapter. We're going to start doing circuits next week. And if you're looking for something to study for the exam coming up, just do any of the homeworks, any of the clickers, any of the discussion things you've done. Those are all fair game so far. Anything up to this point, at least. I will include a little bit of circuits on the exam, which we will go over on Monday and maybe a little bit of Tuesday. I'm not going to put anything from like Wednesday, Thursday on it. That would be mean. Okay. All right. I'm glad you enjoyed it. I'll see you guys on Monday. Peace.